The invention of the wheel, if I may put it this way, invented a mind. And in becoming inventors, we begin to think of ourselves differently. Not simply imperiled by the facts of the world, but perhaps competing with the facts of the world, as in a contest, and a contest that we plausibly now might regard ourselves as winning.
The simple, elegant, yet revolutionary machine called the wheel has literally transformed mankind. Not just in the way we navigate the challenges of our lives, but in the very way we perceive ourselves. Quite a responsibility for a tool so ubiquitous that we encounter hundreds in a day without even realizing it. So simple that we struggle to adequately define it.
I think a wheel is any circular object, regardless of its width, that rolls, and that means it might have an axle to transmit its power to someplace else or to direct its power at a certain point.
Some say an axle is not a necessary component of a wheel.
You can imagine wheels in which the mechanical wheel is not linked to that central axis. For example, in a ball bearing. A ball bearing goes around, it makes a circular motion. It fulfills our definition of a wheel, but it doesn't have an axle.
The wheel and axle is one of 6 basic machines, human-made objects that are the basis of all devices that provide us with mechanical advantage over our environment. The other 5 include the lever, the inclined plane, the pulley, the wedge, and the screw.
You know, it's interesting how some of these machines, it becomes a vague distinction between them. One of my favorite is a pizza cutter. You've got a wheel, the edge is a wedge, and the handle's a lever. So you're using a lever, a wedge, and a wheel to cut your pizza.
Mechanical advantage is important because it allows a single person with limited force to accomplish an otherwise impossible task. Consider the wheeled machine known as a pulley.
Less force is required to achieve a given effect. Now you have to apply the force over a much longer distance, and that's the key. With a pulley, instead of just lifting up a 500-pound block, 10 feet say, you might have to pull 100 feet of rope, but you don't have to apply as much force, and so eventually you get the job done. That's mechanical advantage.
Some have speculated that the earliest wheels were logs, used to transport heavy loads.
I think it might be useful to make clear how little we know about that and to what extent we've made up stories. They're pretty much made up stories. The archaeological evidence for the very first wheel is pretty slim.
Nevertheless, someone somewhere invented a wheel, and in doing so gained mechanical advantage because the wheel reduces friction. Unlike a flat, wide surface such as a placket of wood, which generates a lot of friction, or a sharp, narrow point, the wheel has a smooth, narrow, and continuous surface. It reduces friction because it makes contact on a small, narrow, but endless plane. Plus, the wheel can store energy.
Now that's a very practical consequence of the invention, but there's a much more profound consequence. There's a cognitive consequence. He is now reconsidering the very idea of limitation, because he now has concrete evidence that what he once took to be unquestionably impossible is now not only possible, but practically achieved.
In the ancient world, thousands of years ago, 3 very important achievements of the wheel profoundly and dramatically changed the history of civilization. First, the grinding stone, which ground large quantities of grain more efficiently than an individual with a mortar and pestle.
And both millstones have a groove pattern cut into their faces. The stone above it, not quite touching it, just a little bit above it, rotates. The grain falls in the hole in the middle of the top stone. The grain works its way out along those grooves, and as the top stone rotates, the grooves cross like scissors and shear apart the grain.
Entire communities could form around a single large grinding stone. that might be powered by harnessing cattle rather than human power. Grinding stones were carved out of large rocks, then chiseled into round, flat, grooved discs. Now that grain could be processed in such large quantities, storage became a concern. But the wheel solved this problem too. Potter's wheels used for making clay pots were initially created during the Bronze Age, then later refined by the Egyptians roughly 5,000 years ago. Potters could throw thin-walled pots with great storage capacity in a fraction of the time it took to make a pot without a wheel. Pottery wheels are still used today.
With a kick wheel, you have the wheel head, which is where the potter puts the clay. Below that, there's a shaft, which is connected to a flywheel at the very base. And the flywheel has quite a bit of weight to it, so that the momentum will keep the wheel turning as the potter's kicking and working and alternating.
A flywheel is a wheel with added weight, usually placed at its circumference to store kinetic energy, or the energy of motion.
Basically what it means is the faster a mass is moving, the more energy it has. And you know, if you've got a wheel that's spinning right towards the center, things aren't moving very fast. But towards the outside, for the same amount of rotation, you're moving really fast. So if you put your mass on the outside of the flywheel, it's moving faster, it carries more kinetic energy, and therefore it's storing more energy for future use.
The invention of the flywheel would have a wide-ranging impact far beyond the humble potter's wheel, which would benefit from improvements that included the treadle. In addition to the potter's wheel and the grinding stone, the third application of the wheel, and possibly most significant, was for transportation. Early log wheels evolved into narrow carved wheels that could be connected by an axle. An axle is a structure that is connected to, yet independent from, a wheel. It is often found at the center of a wheel's rotation, or axis. Wheeled carts helped transport goods, for instance, excess grain stored in clay pots. The Sumerians provide the first archaeological evidence of wheeled vehicles. Their chariots, pulled by oxen, date from as early as 3000 BC.
Well, the craft of building wheels, especially in wagons and carriages, to me is very fascinating, because the art of making the wheel, of course, ultimately creates a specialty called the wheelwright.
Early wheelwrights made wheels by carving rims that would be clamped together with crosspieces, with an axle fitted into the hub or center. A leather bearing might be inserted into the hub to protect the axle.
The thing that's most useful to me, I think, in considering the history of the wheel, is that the wheel is only a part of a system. A wheel's no good unless you have a good road for it to go on.
With the onset of carts, chariots, and wagons, roads took on greater importance. Trade routes were established and civilizations could more readily expand. But the wheel did much more than encourage the creation of carts and roads.
It made migration easier and at relatively slight cost. It meant that you could move without being nomadic. You could bring along with you what in Roman times was called the impedimenta. This was the spouse, the children, the relevant family possessions, etc. It meant, therefore, that you could move your culture to another place.
Before long, wheeled devices for transportation were available to farmers tilling the soil, traders transporting goods, and armies transporting soldiers. The Roman road would ultimately be based upon the 15-foot width of two heavy carts, or two columns of troops, side by side.
Once you've got that basic idea of a wheel, then people are very quickly going to figure out all the fascinating applications, whether two-wheeled carts pulled by other human beings, or animals, or wheelbarrows, or chariots, or whatever.
The wheel changed our sense of location, our sense of rootedness. It must have had a chilling effect once these implications dawned on us. To some extent, it still has a chilling effect. It does give rise to the question, well, if I am not meant to be here, now, and abidingly, is there any sense associated with my being meant to be? Or is everything in flux? The wheel really is the device that says no one is ever occupying precisely the same position twice once this thing starts rolling.
Next, wheels rolled across the oceans as vital components of ships. And long-distance trade made the importance of accurate timetables a new challenge that the promise of wheels would solve. Although humans began settling in villages approximately 10,000 years ago, it would be another 5,000 years before archaeological evidence of wheels would appear. The wheel will return on Modern Marvels. During the late Middle Ages, as trade increased partly due to the application of wheels, merchants looked across the seas to new markets for buying and selling goods. Large ships were built, using steering wheels to maneuver the rudder and direct the ship.
As the boat gets bigger, tiller doesn't give you enough advantage, mechanical advantage on the rudder, so you may hook up some gears and shafts or belts and pulleys and ropes, but anyway, you'll have a wheel because it's just so convenient to be able to stand in one spot and control the boat.
Cylindrical wheels called windlasses took up or let out rope to control the sails and anchor. The application of specific wheels often met specific challenges. But the concept of wheels, wheel hood so to speak, seemed endlessly recyclable.
Perhaps the evolution, the changes, the inventions associated with the wheel somehow reflect something very fundamental about us as humans, about how our brains work, about how society evolves over time, and the factors, the influences, the technologies that change who we are and what we do.
Not all cultures, however, have made use of wheels. Despite its technological proficiency, the Middle East eventually abandoned the wheel for transport because the camel better met its needs. So the wheel is not the only solution to every problem.
Today we think the wheel's real important. And it's important to remember that that's not always been true. The whole notion that the wheel and fire are the two most important inventions is a pretty recent idea.
Although the wheel is often not the only solution, it is frequently a tangible framework for seemingly intangible challenges, such as the regulation of time.
We think of the sun as a form of timekeeping in itself, rising in the morning and setting in the evening instantly gives a human being a sense of rhythm and form to time. And so using the sun was an early means of timekeeping by using a sundial.
But sundials aren't precision instruments. As trade and travel increased, the need for accurate and reliable timetables increased with it. Early clocks lacked the necessary accuracy. What was needed and created around the 13th century was the modern wheelworks clock.
Most people, when they think about a clock, immediately they look at the face of the clock with the hands and all the rest of it. That's almost, from my point of view, the wrong end of the clock. If it's a pendulum clock that we're talking about, the pendulum, in fact, is the timekeeper.
Weights suspended from a fixed distance oscillate or swing at the same rate, no matter how heavy the weight nor how wide the swing. Once the pendulum is swinging at a fixed rate, say 60 times per minute, the clock is keeping time. A device called an escapement lowers a weight in discrete measures using specially designed wheels called gears. The gears help swing the pendulum and count each swing through the application of teeth carved into the gear to correspond with the teeth of a another gear.
Gears are really nothing more than a set of wheels in some predetermined ratio, and you put the gear teeth on to be sure that it doesn't slip, but they're wheels nonetheless.
These teeth turned the wheel into a series of levers extending from the hub. 19th century observers even referred to the wheel as the perpetual lever.
In fact, Galileo, in analyzing the simple machines in the 1500s, broke down as all of the simple machines into a combination or a form of lever.
As clockmaking was refined, gears were used to create minute and second hands, greatly increasing the accuracy of the clocks. Gears were made small to fit into wristwatches or large to operate clocks in church steeples. They were even used to trigger chimes using a mallet connected to the gear system or gear train that struck a bell. The principle of accurate timekeeping was applied on a large scale to help navigation. The Earth was mapped out in a series of grids. Each grid measured the distance the sun's light traveled across the surface of the Earth in 4-minute increments, or longitude. With an accurate clock and a simple equation, a sailor could now pinpoint his position anywhere on the planet. Longitude only works if the Earth rotates in a wheel-like fashion.
Now, what would be a more perfect wheel? Well, one more perfect wheel is the wheel-like nature of the heavens themselves, where we see the axle, essentially a gravitational field, and where we see a wheel, now a planet, thus connected to other planets going around in a certain quasi-wheel-like fashion.
And in fact, when astronomers wanted to make tiny models of the solar system, they used a series of wheels in a device called an orrery, in which the planets were on wheels that moved around a central sphere which represented the sun. There's this wonderful progression from the physical reality of a wheel to the metaphor of a wheel in space as planets orbit the sun or as the moon orbits the Earth.
As wheels provide transport to different worlds, they transport themselves into different applications. Technology incorporated the wheel into the printing press, facilitating mass-produced communication by pressing an inked plate onto paper attached to a roller. Wheels were used to give the press constant pressure and to speed up the printing process. Although the wheel wasn't essential to the production of books, it made the process more efficient.
What the book does is it puts thought in a form that allows it to be moved on wheels. It allows one to speak to the world as if the world were a person. And it thus contains within it the possibility of revolutionizing the world without a drop of blood being shed. Not to say that much blood will not be shed, and in fact much blood will be shed because of ideas that are presented in books. But it does mean that you now are capable of persuading without coercing, and in numbers.
From the esoteric to the earthy, agrarian uses for wheels eventually included early windmills, which arrived in Europe around the 12th century. Windmills captured wind using large blades, often covered with cloth, connected to a hub. The hub was attached to an axle that led to a series of gears. The windmill could pivot on wheeled rollers to adjust to changing wind directions. Windmills vary from traditional Dutch windmills to the familiar prairie windmills of the American plains, to the giant turbines that generate electricity on wind farms. Using gear trains, windmills pumped water out of wells, drained swamplands, and even ground wheat. As this 300-year-old Cape Cod windmill, the oldest in the country, once did for the Pilgrims. What's interesting about the windmill, however, is that it harnesses naturally occurring energy rather than human or animal power.
One of the amazing things about wheels is the ability to take energy sources from around us, just the environment, and convert them to useful mechanical energy using a wheel.
Next, the concept of harnessing natural power would spark the Industrial Revolution and create even more ways to utilize wheels. More than 100 million bicycles are manufactured worldwide each year, with a bicycle being a primary mode of transportation in many developing countries. The wheel will return on Modern Marvels. The mills of Europe, and later America, changed the natural environment into a resource to be exploited by the wheel. Nature became another tool for human progress. But the concept of harnessing wind and water actually dates back to the 2nd century BC.
Earliest uses that we know of are water lifting for irrigation and grinding grain, grinding wheat to flour.
Water wheels harness water power in different ways.
One is an impact water wheel, commonly called an undershot water wheel, where the water strikes a flat paddle and the impact causes the wheel to rotate. A second type of water wheel is called an overshot or a weight-driven water wheel, where the water comes over the top of the wheel, descends into a bucket, and the weight of the water in the buckets on one side of the wheel causes it to turn.
At the beginning of the 12th century, England had more than 5,000 mills, each one a community power plant for a host of otherwise burdensome tasks far beyond just lifting water and grinding grain.
European technicians and concurrently Chinese technicians diversify the use of water power to where by 1500 they know how to use water power for pounding metals, to shape metals, for pounding ore prior to reduction, for grinding a whole host of things other than wheat.
Rivers, abundant in the northeastern United States, would provide an accessible source of power during the early days of the nation.
There are a whole lot of rivers and streams that drop a fairly great distance, and the Industrial Revolution in America really takes off based on water power, particularly in the countryside.
Villages and towns dug canals and built mills to saw wood, spin wool, and grind grain.
On top of the millstones you have a hopper, big wooden funnel that holds whole dried grain, be it wheat, rye, corn, barley. And below that there's a shoe, a little wooden trough that directs the grain from the hopper into a pair of millstones. There's a vertical wooden shaft called a damsel that rotates with the millstone and shakes the shoe.
This process is possible because the water wheel is connected through an elaborate system of gears and flywheels to the millstone, or whatever the mill was assigned to do.
It represents a sort of quantum leap in the amount of energy that humans were able to extract. A human being can produce about 1/10 of a horsepower continuously over a 6 or 8 hour day. That means even a small 2 horsepower water wheel is producing 20 times as much energy as a human being, and it doesn't get tired.
Water mills are an ingenious use of available resources, and by simply reversing the concept of the water wheel, you end up with something entirely different.
One of the neat things about wheels is the way you can turn this energy conversion around. We have water wheels that produce energy of all sorts, whether it's electrical energy or energy for a grist mill, but put it on a paddle boat, connect it to a steam engine, and you've got a paddle steamer. So it works both ways.
The paddle wheel of a paddle steamer can be thought of as a series of oars attached to a wheel. Robert Fulton's paddle boats began plying the Mississippi in the early 19th century. But the business end of a paddle steamer is really the steam engine that generates the energy to move the paddles. And here again, the concept of the wheel manifests itself in an aptly named mechanism called the sun and planet gear. The planet is a small gear that orbits the sun, or gear connected by an axle to a driving wheel. As steam is forced into a piston chamber, it expands and moves a lever attached to the planet wheel, which is in turn connected to a spoke coming from the sun. The sun then moves the driving gear. The principle of the sun and planet gear is well illustrated on another transportation device that revolutionized the world, the steam locomotive.
At certain times in American mechanical history, rotary devices seem to be the way to solve all problems. So for a while in the 1840s in particular, you have all these very, very clever rotary steam engines.
Trains obliterated frontiers in America in the mid-19th century. The entire country was crisscrossed with track.
There were companies that manufactured car wheels, usually the axle and the two wheels to go into railway cars, but locomotive wheels would be built right along with the rest of the locomotive as heavy castings and then turned on a heavy lathe. And usually the wheel itself would be cast steel, and then there'd be a forged steel tire, and the tire would be expanded with a little heat and then put in place and then allowed to cool and shrink down tight.
With the advent of trains, wheat could be grown in Kansas, shipped to Chicago, and be ground, then packaged and distributed to New York or California, all mobilized on railroad wheels. As railroads regulated the nation, they helped grease the Industrial Revolution, providing markets for goods more efficiently produced because of the wheel.
The part of the wheel in the Industrial Revolution is central, not only as it influenced factory production, but in fact as it made possible the steam locomotive and a veritable empire that will depend on the movement of troops, the movement of people, the crossing of entire continents in periods of time heretofore unimaginable. The Industrial Revolution, in fact, rolls inexorably on wheels.
Next, by the turn of the 20th century, this inexorable roll would generate even more wheel-based innovations. The number of locomotives in the United States peaked at nearly 70,000 in the early 1920s. The wheel will return on Modern Marvels. As wheels harness natural power, they liberate us from otherwise exhausting or impossible tasks. But the idea of the wheel as liberator took an ironic turn in places like Lowell, Massachusetts during the mid-19th century. With its textile mills full of machines operated by young farm girls. Textiles had for centuries used simple hand-operated spinning wheels to twist cotton, wool, and flax into thread. But wheel-based innovations at the turn of the 19th century increased production.
The vertical spinners or jennies came in. Again, it was an effort to get more production with one worker. And so there are 10 spindles, all run by one wheel.
Eventually, single machines spun 200 spindles of wool at the same time. Planned communities like Lowell formed to produce textiles along rivers like the Concord and the Merrimack, which generated roughly 10,000 horsepower to Lowell's water wheels.
It was an interesting social experiment to bring in the farm girls, and they thought they were being liberated from the hard work of the farms, only to discover that life in the mills could be long hours, and that the hours were ruled not by the sun but by the mill bell.
What the Industrial Revolution did for women was that it rendered them to some extent independent of marriage. It made self-support possible, but by creating an entirely unliberated world of incessant labor, discomfort, and the conversion of oneself into a kind of instrument or tool.
A cog, if you will.
success of our machinery has convinced us, almost to a person, that there is no problem so great that some machine can't solve it, and to that extent we do tend to look for mechanical solutions to problems that are not mechanical.
The inexorably spinning wheels of the Industrial Revolution produced an inexhaustible supply of products, including more wheels. Despite our constantly reinventing the wheel, the concept of the wheel hasn't really evolved, a testimony to its simple purity. But in practice, wheels do evolve. They improve through technology and materials. The log evolved into the carved wheel, which became the lighter, more efficient hollowed rim with spokes and a hub. The tire evolved from a metal casing into something altogether transformative with the advent of the automobile.
Because of speed and heaviness of a car, you've got to look differently at a vehicle that's going, say, 5-10 miles an hour drawn by a horse on the rugged roads of the 19th century. You've got a car that's capable of 20 miles an hour, you've increased the stress on the wheels about 4 times, and your old wagon wheels begin to fall apart.
The automobile itself was another collection of gears. Crankshaft and steering wheel, ball bearing and transmission, all rolled out on an assembly line. Again, a variation on the wheel. But of all the wheels connected to the car, the greatest may be the pneumatic tire. Tires were originally just cloth or leather coverings wrapped around a wood or metal wheel to provide cushioning. Eventually, hard rubber was used. Finally, pneumatic tires, which trapped a cushion of air inside the tire, were employed, initially on bicycles. But by the early 20th century, they found their way onto cars and trucks.
Air is the most efficient thing that'll carry the load and give you cushioning, and you need certain footprint characteristics, force and moment characteristics for the tire, and the deflection of the tire will provide that and gives you very even distribution of load across the footprint with just air in the cavity.
Before air could be pumped into a rubber tire, the rubber had to be hardened, made impervious to changes in the weather. In 1839, Charles Goodyear, an inventor, searched for an additive that would keep rubber from turning brittle in the cold and sticky in the heat. He stumbled upon vulcanization, a curing process that basically cooks rubber until it stabilizes and holds its shape.
So he had a lot of different chemicals that he was experimenting with, and he accidentally spilled some of the sulfur on the stove, and sulfur will melt. And under those conditions, and he had some rubber laying on the stove, and it ran together, and it vulcanized, lo and behold.
By the 1950s, synthetic rubber had replaced natural rubber. Tire companies like Goodyear really were reinventing the wheel.
Again, the ideal wheel, the round thing that's frictionless, that's not something that gets better. But the practical wheel, the wheel that gives better mileage or brakes better or is lighter, that's the point where you can spend a lot of money and over the years get a lot of improvement in efficiency.
Today, making tires is a complex and highly specialized endeavor.
There are up to 15 different components in today's steel-belted radial tire. You have the beads, the plies, there's wedges, apexes, liner, sidewall, tread compound, sidewall compound, overlays. There is some ongoing innovation work with tires with computer chips in them that will read the road, that will help control the vehicle. They will be an integral part of the vehicle control system, and they'll be reading it from inside the tire, which is a great advantage since it's closer to the road.
Goodyear manufactures tires for all sorts of vehicles, including off-road, earth-moving equipment, farm vehicles, and airplanes. Airplane tires endure particular stress during takeoffs and landings because of heat caused by the friction from the weight of the cargo and the high speeds needed to achieve lift. Wheels play an indispensable role in the aeronautics industry beyond tires. The propellers that first lifted the Wright brothers off the ground used the principle of the windmill, only in reverse. An axle from the center of the propeller connects through a complex gear system to an engine that supplies the spin. Instead of harnessing wind, a propeller generates it, lifting the plane off the ground. Switch the propeller from vertical to horizontal, and the wheel elevates the helicopter's rotary blades and elevates us from our earthbound existence, free and unfettered, thanks to wheels.
I think there's a continuum here of mobility, if you will. And along with that mobility, I think, comes a lot of the basic freedoms that we, again, sometimes take for granted. The right of free assembly depends on free transportation, free mobility, at least certainly transportation free of any political hindrance.
Next, the impact of wheels extends far beyond the immediate benefits we reap. But are there other applications for wheels that we haven't even conceived of yet? Other materials in which to forge them? Other ways to experience them? A typical tire manufacturing plant can produce approximately 25,000 tires in a single day. The wheel will return on modern marvels. If the airplane propeller is a variation on the windmill, then the jet engine is a variation on the turbine, which was originally a type of water wheel.
Water turbines are essentially water wheels with curved surfaces. They produce power by water flowing smoothly over a curved surface because the water acts over their entire surface simultaneously instead of on only one paddle or one bucket at a time. They produce much more power in a much more compact form.
Hoover Dam makes use of over 17 14-foot wide turbines to generate 2,991,000 horsepower, which is then transformed into electricity.
Moving magnets create electricity. So in every turbine, you have coils of wire and you have magnets. And as you turn those coils of wire in the vicinity of a magnetic field, that's what produces the electricity that we use in our homes. Now you can generate that circular motion with a water-driven turbine, a water wheel. You can generate it with steam in a coal-burning power plant or a nuclear power plant. You can generate it with wind.
Jet engines replace water with air inside the spinning turbine. And instead of electricity, jet engines generate thrust as the air is pushed out of the engine, lifting the plane. From the circular motion of a spinning turbine to the spinning of a disk drive running a computer, we spin our wheels everywhere. The CD-ROM is similar to the compact disc, which harkens back to the old vinyl record and turntable, which was a variation on the ancient hurdy-gurdy. In the future, we may need a microscope to see our wheels.
One of the great frontiers of the wheels has to do with making them small, making them microscopically small. This is nanotechnology. Right now, we can use lasers, we can use various other techniques to fabricate tiny pieces, including wheels and gears that are 1/100th the diameter of a human hair. You can make gear systems, gear trains on a surface that you need the highest power microscope just to see them. Now, these aren't machines yet. These are just demonstrating the feasibility of doing it. But imagine a society, imagine an age when we have micro machines that can build other machines. Micro machines that can do surgery on our bodies. Micro machines that can fabricate microelectronics, make your computers smaller, make them more powerful.
Wheels invaded every aspect of our lives with their undeniable utility and practicality. And perhaps they've made us practical too. But there's another wheel that's important to us, a wheel built solely to amuse.
To talk about Ferris wheels and balls and things like that as pointless, mere games, sort of life's trifles, I think we grossly underestimate the power and force, the imaginative potential, the discipline of the mind wrought by such trivia as Ferris wheels.
After conquering so much of life's work with wheels, it's reassuring to acknowledge the importance of play, and of the wheel's importance to play. Ferris wheels, despite their frivolity, are actually complex wheeled mechanisms requiring precision engineering. The largest Ferris wheel in the world is the Millennium Wheel in London, opened in February of 2000, with a diameter of 443 feet. But the first true Ferris wheel was a giant as well, built for Chicago's Columbian Exposition of 1894 by George Washington Gale Ferris, an American engineer who understood steel.
It was first rejected out of hand. It's too wild and too improbable. So nothing else was forthcoming, so at the last minute they got a hold of Mr. Ferris and said, okay, we'll go with your idea.
Ferris produced a 250-foot diameter steel wheel that rose 264 feet off the ground at its highest point. The giant axle was a single forged piece of steel, the largest single forging accomplished at that time. 2 steam engines powered the wheel that carried over 2,000 passengers on a 40-minute journey through 2 revolutions.
The first time you just got over your fear of sitting there hanging on to the seat, and the second time you got to look out and enjoy the ride.
One enthusiastic customer was Lee Sullivan's grandfather, William E. Sullivan, who talked the wheel's operator into letting him observe the mechanism that drove the wheel.
When he came home, he told Grandma that that's what he wanted to do, build wheels. She said, well, don't tell anybody, they'll think you've lost your mind.
Lee's grandfather turned his Jacksonville, Illinois bridge building business into a wheel-making one. More than 100 years later, it continues as the oldest Ferris wheel manufacturer in the country. It's a long journey from the grinding stone to the Ferris wheel. But the story of wheels is an endless variation on a simple theme.
And so our inventions change us. They don't just make us more powerful. They make us think differently about the same sorts of things. They make us think differently about the role of thought itself.
You think about how much the wheel has driven society, how much it's increased a single human's ability to do more work, to get places that humans could never get before, to travel greater distances, to do technologies you never could do before. Just the ideas of things you could do with gear systems, things you could do with water wheels, things you could do with transportation. It's transformed society.